complex numbers. I used to have the math anxiety that a lot of you have, especially when you take tests, right? It's an anxious time. But part of that anxiety is caused by the jargon. So don't let the complex numbers scare you. The goal is to simply add, subtract, multiply, and divide complex numbers. The 4 operations, right? Yeah, that's familiar territory. Okay, let's start off with a question. Here's the question. Is there a solution to the equation x squared plus 1 equals 0? In other words, is there a number x you can square, add 1 to it, and get 0? Well, if you use the techniques that we've developed for solving this equation, you'd have to isolate the x squared. What would you get on the right side? Negative 1. So it's equivalent to asking, is there a number I can square and get negative 1? There's no real number I can do that with, right? 1 times 1 is 1. Negative 1 squared is positive 1, right? Everybody see what I'm saying? There's no real number you can square and get negative 1. So the answer to the question, you might think it's no. But I'll say it this way, not unless we make one up. So that's exactly what we're going to do. Okay, we're going to make one up. And you might think, well, now he's great. Now the teacher's making up math. What good is that? Well, it actually does a lot of good. These kind of numbers we're talking about today are used all the time in engineering, particularly electrical engineering. We're not going to get into those applications, thankfully. Most of you probably are thinking. But yeah, anytime you analyze AC circuits, this number I'm about to show you is going to pop up. It's called J in electronics, but or in electrical engineering, but we're going to call it I. So here's the definition. You could do it 2 ways. You could say I squared is negative 1. So that's the made up, I then is the made up solution to that equation, right? You plug I in for x, you get a solution to that equation. But more specifically, we're going to say I is the positive or principal square root of negative 1. So that's usually the way we think about it. Now, unfortunately, I is called the imaginary unit. Now, why is that unfortunate? Well, because imaginary kind of makes you think that it's not good for anything, right? But the imaginary number I is good for a lot of things, not the least of which is what I just mentioned, AC circuits. So it's just one of those things. It was called imaginary, but it has a lot of uses in math. So by the way then, just taking that equation, x squared plus 1 equals 0 then, the solution, it actually has 2 solutions. I, and really negative I, right? So if you put I in here and in for x and square it, then I squared by definition is negative 1, and negative 1 plus 1 is equal to 0. So that's one of the solutions. And same thing if you plug in negative I, because the negative squares out. The initial negative squares out anyway. So there you go. Now we made up a solution. I is not like any number you've ever seen before. It only has 4 unique powers. So let's think about this. Everybody would agree that I is hopefully equal to itself, right? Any number is equal to itself. I squared, as we've already defined, is equal to negative 1, right? Okay, what would I cubed be then? I mean, it's I cubed, right? But it simplifies. Because if the powers, if the laws of exponents hold, then I cubed means I squared times I, doesn't it? Just by definition of what an exponent means. But what is I squared? I squared is negative 1, so negative 1 times I would just be called negative I. So I cubed is equal to negative I. That doesn't happen when you cube 2, right? 2 cubed is not negative 2. 2 cubed is 8. So this is a weird number. It should strike you as strange. This is not a number you would count apples with, is it? No. You don't have negative I apples or I apples. But then again, you don't count apples with negative numbers either, right? Didn't negative numbers seem really strange the first time you saw them? Yeah, they did to me. I didn't like them at all. But you can't deny their usefulness, right? If you have negative $500 in your bank account, that tells you something, right? You're overdrawn by $500. So negative numbers are useful, even though they're not useful for counting apples or objects. And it does turn out that I is useful, but it's not useful for counting just objects. Okay, I to the fourth. How could you break up I to the fourth? Well, that would be I squared times I squared would be one way to write it, right? But what is I squared equal to? Negative 1. So what's negative 1 times negative 1? 1. So you start off with I to the first power. You get, I didn't write it that way, but I to the first power is I, right? And you go to I to the fourth, you get 1. What's going to happen then if you go to I to the fifth? Well, one way to write that would be I to the fourth times I, right? But what's I to the fourth? 1. So 1 times I should hopefully be I. So look, we've gone all the way around. We started out with I. We started taking successive powers, and we got to I to the fifth, and we're back to I again. So what that really means is there's only 4 unique powers of I. We're going to assume that I to the 0, by the way, is equal to just 1, in case you're interested in knowing that. But that's the same as I to the fourth, right? I to the fourth is equal to 1. So there are only 4 unique powers of I. So that should strike you as weird. So that means if I have like I to the 92 power, that should reduce to one of the 4 powers of I, right? Now, what would be a simple way to reduce that? Well, if you think about it, if you took this 5 on the I and you divided it by 4, 4 comes from the fact that there are only 4 unique powers of I, and you look at the remainder, that's going to be the reduced power of I. So 4 goes into 5 how many times without going over? 1, right? Do the long division. You get a remainder of 1. But that's exactly what the reduced power on the I was. That's what's left over when you take out those extra factors that are equal to 1, essentially. So what does that mean? Well, that means we can reduce any power of I. So simplify I to the 42 power. Basically, you need to take 42, divide by 4, and the remainder is going to be the reduced power on the I that I to the 42 reduces to. So how many times does 4 go into 42 without going over? 10 times. Okay, 4 times 10 is what? 40. What's the remainder? 2. That's the reduced power on the I. So I to the 42 is exactly what you just said. I to the 42 is I squared, but what's I squared? Negative 1. So believe it or not, I to the 42nd power is just negative 1, the number negative 1. Pretty trippy, huh? Okay, let's try I to the 91. Well, you guys try it. Take 91, divide by 4, tell me what the remainder is. Well, okay, take 4 into 9 goes how many times without going over? Twice. So start there. Bring down the 1. What's the remainder going to be? 3. So I to the 91 is really equal to I cubed. But wait a minute, I cubed reduces. What was I cubed equal to? Negative I. So believe it or not, I to the 91 is equal to negative I. Okay, so you need to know those 4 powers of I, right? The 4 unique powers of I that we listed here. I to the 1, of course, is I. I squared is negative 1. That's the most important one. I cubed is negative I. And, of course, I to the 4th, you're back to 1.